Go. Okay, so where we left off. Oh. We were talking about light and atoms. Right, now I'm gonna... Alex F., what is the last thing we learned? Mm-hmm. Okay, so yeah, the take-home ideas from the end yesterday was about the or 2 days ago, about the photoelectric effect Alex just laid out for us. That in order to eject electrons from a material, we saw was completely wavelength dependent. It had nothing to do with intensity. Once we hit that critical wavelength or went below it, if we upped the intensity, it just meant more electrons would come out, right? But in order to get an electron to be emitted from our material, you needed to have a specific wavelength or below. So, why does this mean that light is a particle? So, what scientists theorized were, in order to eject the electron, light wasn't acting like a wave, it was acting like a photon. Electron. Photons were required. And we think of a wave as like a continuous thing, right? But photons are individual particles of light. So individual particles of light could eject electrons, but not waves. Because if it were based on a wave, then the intensity would be the important thing, right? So we saw that it wasn't the intensity that matters. It wasn't the size of the wave that ejected an electron. It was just the frequency of the light. So because of that, scientists said, okay, it has to be an individual particle of light that hits it. So by increasing intensity, what are you merely increasing? If we're looking at light as a particle, we increase intensity, what does that mean? Yeah, more particles. Increasing intensity means more particles. So, moving to, and this is just sort of an addendum that I wanted to add onto this slide. Moving to lower wavelengths, any excess energy is, goes into the KE of the emitted electron. So, on your problem set, you're going to get a question about this. I believe you're going to have to figure out what the excess energy is, or the kinetic energy is of an electron that gets shot out of a material. Is that a question, Noah? So why can't waves eject electrons? Well, if waves were what was required to eject electrons. If you increase the intensity, that would mean bigger waves, right? And you would expect bigger waves can push an electron out. But that's not what they found. They found that the size of the intensity, the amplitude of the wave didn't matter. That it was just the wavelength. So the question was, what does wavelength correspond to? And you're about 2 slides ahead. So we'll get there in 2 slides. Okay. That was good, like, what's the word? Foresight? Prediction? Okay. So, oh wait, did I hear a wait? Okay. Yeah, no, take your time. You can use fancy words for that too, aren't there, like oracles? So the question was about the resonant frequency. So we're more looking at the different energy levels within an atom, and I'm going to explain a little bit in a minute. Right, this is the question was, are we ejecting electrons and not the entire atom? Yes, we are ejecting just electrons. Just electrons. Okay. So in order to be a famous physicist around the turn of the 19th century, you needed a mustache. So Planck, I always call it Planck, and then Mr. Hamill has sort of a background in German, so he made sure I say it's Planck, I guess. And Einstein, they came to the rescue, and they merged the particle and the wave together and said, hey, light can be both. Light can behave as both a wave and a particle. And it turns out electrons can behave both as a wave and a particle. So your take-home message is scientific experiments showed that light acts as both a particle and a wave. So the wave, the evidence we have for the wave is the interference pattern from the double slit experiment. The evidence that light is a particle is that it takes a specific wavelength of light or lower to eject an electron from a material. So evidence supports both. So we have light like this, and then light like this. Yeah, Nathaniel. So the question is, does that mean it is both, or if it's is it just something that we don't know or can't understand? I'm going to go with ask someone smarter than me. So for this class, you don't need to know. I don't truly grasp all the nuances of the particle-wave duality. But for us, even in college, until you get to higher level, much higher level, above what I took just in electromagnetism and electromagnetic waves, it acts as both. Right. So the question is, when you get to electron particle wave duality, you're looking at wave functions, and as soon as you observe, like the eye from Dr. Quantum, as soon as you observe that, you take all these probabilities and you collapse it down to a single probability. That's when the wave becomes a particle. With light, I don't know if it quite works that way. I'm not sure. It might, but I'm not positive. Yeah, it's hard to observe a photon, although you can stop it now. We've been able to stop light in different media, or you get like super, super cold, low temperatures, and you can trap light temporarily. Okay, so here is the question about energy, frequency, and wavelength. So at the time, they just saw that the wavelength, so you needed a specific wavelength or below. It turns out energy equals H, and we're just going to use, let's just go easy. We're not going to use the symbol that you might see. Does anybody, you're right, we're not going to use lambda's wavelength, right? Frequency is, you might see it written like, I think it's this. Guys, check your blue formula sheet. You're going to have it for every test, so you should get to know it. How is this written on your formula sheet? Yeah, so on your formula sheet, it's written like this. Right. So I like to write it in a way that's easier to understand. Does anybody know what the H is? Yeah, Planck's constant, or Planck's constant, or... Does anybody speak German here? Is that even close?
Planck's.
All right. So, okay. So, I might just go back to saying Planck sounds more French. Okay. Yeah, I don't want to be disrespectful of the guy. You know, he had a lot to give to science. So I'm going to try my best to pronounce it, but I have a terrible ear for tone. So, this guy's constant. All right. So, constant. And the great thing about his constant is you can always find it on your blue formula sheet. So, what is his constant? It should be on that sheet, right? And what are the units? Units are important. Joules times second. All right. Okay. So, what this equation states is that if you have the higher frequency of light, your photon has more energy. But how do we relate wavelength to frequency? Turns out there's a wonderful equation that allows us to do that. I'm going to write it out because it's written in a different way on your blue formula sheet. How is this written on your blue formula sheet? Yeah. Lambda. I hate. So guys, English is a terrible language because you can pronounce so many things so many different ways. I would not want to. It's really hard. It's so much harder to learn English than most other languages, just because of all the tones. So C. The question becomes, what is C? It turns out C is equal to the speed of light in a vacuum. So this is the speed of light, which is equal to 3. I'm not going to put the decimal points in. 3 times 10 to the 8th meters per second. So if I know the wavelength of my light, all electromagnetic radiation travels at the speed of light. This is going back to freshman physics, right? So all electromagnetic radiation travels at the speed of light, which is 3 times 10 to the 8th meters per second. If I know my wavelength, I can plug it in for lambda and get my frequency and solve for frequency. So you might see it, a way you're going to use it a lot is this. Its frequency equals the speed of light over lambda. So then, you take the value you get for frequency and you plug it in here. Since this guy's constant is always the same, once you get the frequency, you just multiply it by the constant and you get the energy of your individual photon of light at that wavelength. So the question is, when a photon has more energy, what does that mean for the photon? Well, it's traveling at the same speed, right? So it just means it can. So how do we measure energy? Yep. Okay, so now we're getting into some. So how can a photon have kinetic energy if it doesn't have mass? Light doesn't have mass. Don't worry about that. Like, just know that you're going to plug in here. What unit do you think you're going to get here? You're going to plug in here. Yeah, you're going to get joules. So that joules is the amount of energy that that given photon has. And so that photon can do work on a system. Now, even with, if you look at Planck's constant, now I'm just totally lost. All right, if you look at his constant, you're multiplying by 10 to the negative 34 joules. So even if you have a very high frequency photon, it's still not going to have, an individual photon is not going to have a huge amount of energy by itself. So you can eject a single electron, but in order to get more electrons, you just need a much higher intensity. So you need a lot of those photons, each of which has that given energy. Okay. So frequency and wavelength is what determines the energy of a given particle of light, which we happen to call photons. Does anybody watch old Star Trek episodes? They like use the photon torpedoes. Yeah. So they're basically just shooting light. I don't know how it works, but okay. So this brings us to the electromagnetic spectrum. Now, we start with radio waves. It's a good thing radio waves do not carry with them a lot of energy because they're all around us. We couldn't use the radio or else we'd be bombarded with these high energy waves. But radio waves have a very long wavelength, which means they have very low energy. Eventually that will come up. Maybe? No, okay. Oh, wow. Low energy. Not low energy. Low energy. Okay. I'm going to erase that. So, now the question becomes, radio waves have the lowest energy. Microwaves have the next lowest energy. Microwaves have less energy than the visible light that we see. Yet, we put our food in them and it cooks. Why is it that microwaves can cook our food? Phil? Yes, so what microwaves do is water absorbs the microwaves and they start vibrating. And when things vibrate against one another, what do you get? Friction, and the more friction you get, the more heat you get. So microwaves in and of themselves don't have much energy. But because water vibrates when they're exposed to microwaves and they rub the water molecules rub together, you can get your food heated up. Yeah, you also don't want to put like metal in a microwave, right? What happens if you put metal in a microwave? Yeah, it's bad. Well, so different things can happen. I will say, luckily, by the time my kids grow up, there won't be CDs anymore. Has anybody ever put, this is a do not ever do at home, look it up on YouTube. Has anybody ever put a CD in a microwave? So those of you watching at home, I'm going to, oh no, I can't pause it. All right, well, let's just watch it. I'm saving you guys at home time. All right. So, YouTube. Oh, like CD. I know because I mean, I have never done this ever in my life. Okay. Yeah. Right. Okay, so it's really dark. It's hard to see. Okay, yeah, good. We got some light. Yeah. I don't know why this is the best one ever. Okay. It doesn't last very long. So that's why you don't do that at home. I showed it to you here, so you do not do it at home. You'll ruin your microwave by doing that. So don't do it, but I think it does look kind of cool, right? You get a little lightning show. I don't know why that happens, to be honest. Okay, so now we get to infrared. So our energy, we're going from lower energy. A little sneak preview. All right, lower energy to higher energy. We're going to talk about infrared later on in this lecture, what it can be used for. As scientists, as chemists, we actually use infrared light to determine a lot about molecular structure. Then we get to visible light, Roy G. Biv, which you guys saw when you did the lab earlier this week, right? We saw that our solution absorbed light at a certain frequency, did not allow it to get transferred. UV light is dangerous for people who have my complexion because my skin does not block UV light very well, which means it can damage your DNA. So there's enough energy in UV photons that it can actually it can damage your DNA. It can change the chemical makeup of your DNA. So you hit it with a certain amount of energy, you can eject an electron, you get free radicals, and the free radicals are bad. So, and then X-rays, very high energy. We use them to actually look into our bodies. And then gamma rays, if you're exposed to gamma rays, you turn into the Incredible Hulk. Or you get cancer, which is probably much more likely. These things are not as much fun as they are made out to be in comic books. If you get hit with gamma rays, it's very, very bad. Very, very bad. So a lot of the fallout from Hiroshima and Nagasaki, the radiation came from this, and it caused all kinds of burns, and then later cancer. There's this whole sort of subculture in Japan of the survivors of that and how they were ostracized by the community. It's really terrible. Why are there 3 boxes for radio waves? There are different, like, FM, AM, and like there's another one that I don't remember what the name is. But it's split up into different, like, really long wavelengths. Some of these have the wave of like multiple meters of wavelength. So it would be, the wave would start here and end at the other side of the room, which I think is kind of cool. Okay, so just have an idea of the electromagnetic spectrum. You should know this. I hate making you memorize things, but this is something I feel is quite important. So here's another view. Radio waves, size of humans on the really, really low energy, long wavelength. You can get size of buildings. By the time we hit visible, we're down to the size of, very small single-celled organisms. So the light that we're seeing right now, the light that our eyes has evolved to take in, is of the wavelength of protozoan. And then as we get down to really high energy gamma rays, we're talking about something that has a wavelength the size of an atomic nucleus. So the electromagnetic spectrum encompasses a very wide range of wavelengths. And this just gives you some sense of how to relate them to different things. Okay, so I need a volunteer to be, I think that's Foxtrot. Nobody? Oh, all right, I'll read it then. Okay, so do you sell ultraviolet bull? Excuse me? How about regular violet bull? No. Blue bull? No. Green bull? Yellow bull? Orange bull? Rats, I'll take a red bull. I was hoping for something a little higher energy. I hope it's not. At least it isn't infrared bull. It's so funny. So cheesy jokes. We trade in cheesy jokes here. Okay, so now I want to show you guys something at home. Unfortunately, you're not going to be able to see this. If you'd like to come to an X block, I can show you. But this is a lot of the information we get about quantum mechanics and atomic structure comes from light. So it turns out that if you apply a voltage to a sample, Oops. This one has not been opened yet. Okay. Sample of a given material, it can emit light, and that light emission is sort of like a fingerprint of that element. All right, so let's see. Okay. So what I'm showing the class right now is a hydrogen emission tube. It's hard. I guess everybody can't see it. I'll do like my modeling of it. So what do you guys see? Pink purple light. Yeah, it's a nice pink purple light. Looks a little bit like a neon light, right? That's how neon lights work. You send a voltage through and you excite the atoms. But why does it create light, and how does that light come to be something you can see? So hydrogen, the most simple element on the periodic table. It turns out that if you shine white light at a sample of hydrogen, so white light, what we get from the sun, a wide variety of wavelengths, like the entire spectrum. And then you measure what gets absorbed. There are specific bands. Specific absorption band. Not bond, band. Bless you. So, scientists were confused. Why did hydrogen only absorb light at those very few wavelengths, those very few colors? Then, if you apply a voltage to a sample, it turns out that it emits light at those exact frequencies that it absorbed from the white light. So let me just write up here. White light is comprised of all wavelengths of the visible spectrum. Now, so hydrogen emits at 1, 2, 3, 4, 5 different wavelengths. Did you guys see light with 5 individual wavelengths? No, you guys saw something that was like, ooh, let's see what's the closest color I can come to on our color palette. What do you guys think? Like, that's a little dull, too dark. Maybe I'll add a little. No, that's, yeah, they don't mix. They just go right on top of each other. Okay, yeah, why did I think that would even work at all? Okay, so probably closer to, no. Come to X block, or come at some point, and I can show you exactly what color it was. Yeah, oh, a highlighter color. Highlighter. Yeah, highlighter's just yellow. Yeah, I was trying to do the hydrogen color. Magenta, okay. At home, for those of you who are attuned to colors, it's like a magenta. So, if you apply, the take home is, you apply a voltage to hydrogen. What you see is a mixture of these wavelengths that are emitted. If you took a scope that could split the light and bend the light, so you get this light that comes out, right? Now, if you, say you put it through a prism. Do you guys know what a prism is? So you put it through a prism. When I was in high school, most people knew what a prism was because it was the cover of a Pink Floyd album. So it goes through, and then it splits, and I'm not going to be fancy enough to do all the colors. It splits into its individual wavelengths. Right? So scientists took the light that came from the hydrogen emission spectrum that they saw as magenta, put it through a prism, and split it into its individual wavelengths. Why do we care? Other than it's neat, why do we care? So, again, I don't have the slide on my notes. You get a continuous spectrum from light from the sun, certain kinds of light bulbs, you get a continuous spectrum. From hot gases, the electrified gases like I showed you in hydrogen, neon lights. Oh, sorry, what do the words say? This says continuous and this is just spectrum. This is the emission spectrum, where we made the gas hot by applying a voltage, and if you put it through the prism, this is what you'd see. And then if we put light on a cold gas, we get the absorption spectrum. So, now, why we care. This is the why we care. And really, this is why we care about light. One of the main reasons we care about light in chemistry at all. So, the atomic emission spectrum for hydrogen is well studied. So, it's broken into sections based on types of emission. So we have the Lyman series, which we can't see, right? We can't see ultraviolet light. These are the very high energy absorptions or emissions. We have the Balmer series, which is the one that I just showed you. You do not need to remember these names. I don't remember these names. I just read them when they come up on the notes. I understand that there are 3 different ones, though. And then you have the Paschen series, which is low energy. So hydrogen absorbs all kinds of different light, or can emit all kinds of different light when electrified. How can we explain it? So let's say we're applying energy to hydrogen. We're applying a voltage to hydrogen. So the electrons absorb the energy. So electricity, kinetic energy, they absorb the energy and it becomes potential energy. This is after you apply the voltage. Now, because the temperature is not changing at steady state, we know that it's become potential. So I have a positive nucleus, a negative electron. Potential energy is increasing. What does that mean? Yeah, go ahead. So the electron is moving away from the nucleus, right? We know that when things are attractive and they have higher potential energy, they're further away from each other. So what's happening here is that electrons are promoted. It's like, I don't like the word promoted. I also say move up. Promoted, I think of like jobs, but promoted or moved up to a higher energy level. So the sample absorbs light at a given wavelength. It promotes an electron to a higher energy level. The electrons relax. And when the electrons relax back to their original energy level, what happens? It emits light. Electrons relax, the potential energy is converted back to kinetic, and light is emitted. Yeah, this is for the emission spectra. Right, so light is emitted at one of the emission bands on the spectrum. So it's not always going to be the exact same band, because it can get promoted to a higher energy level and then fall back down like one step at a time. But they will be on that spectrum. So the fact that the spectra showed only specific wavelengths, right? There are only 5 in the visible spectrum that we could see. And they were very, very specific, right? So specific bands show that electrons, and I'm just going to write E minus for electrons sometimes, are in specific energy levels. And you're actually on the problem set going to look at the transition between some of those energy levels. So, just an example, you have a hydrogen nucleus, and you have an electron in the first energy level. It absorbs light. It gets promoted out to a much, let's just say it gets promoted out to a much higher energy level. What I was saying with Izzy is it does not have to go back down immediately from a higher energy level right back to the beginning. It might go back it might fall back here. And if it falls back here, it releases, wow, that's some ugly light, and that's not at all at the same wavelength. I don't want to build in misconceptions. Okay. So, it will release light at a given wavelength. That's much better, I think. Okay. And then maybe it'll fall down, maybe back to the beginning, and it'll release light again at a specific wavelength. So by looking at these energy transitions, we can determine a lot about the structure of an atom. So when you watch the notes about electrons, maybe the lectures about electrons, maybe some of you have already started, talking about energy levels. This is how we know energy levels exist. It's through the absorption and emission of light at different wavelengths. Now, things you should know. Spectroscopy. There's a lot. I'll read through it. This is Things You Should Know 2.8. We use spectroscopy to study atoms and molecules. Basically, you're shining light at a sample, and you absorb which wavelengths get absorbed. You guys did this in your lab the other day. Now, there's a couple different types. The first type is infrared spectroscopy, where you shine infrared light at a molecule. It absorbs that light, and it makes them vibrate more quickly. So really what this tells us is information about the bonds that are present in atoms. Then we use visible and ultraviolet light to make the electrons move to a higher energy level. So this gives us information about the arrangement of electrons and energy levels. Certain compounds, like the one like dyes, you're actually studying the absorption there to get a concentration. So let's look at infrared spectroscopy. Okay, so I'm going to add in some very important words here. It should say bonds in molecules can vibrate at different speeds. And these speeds are specific to the bond type. Because we're running short on time, I'm not going to click on this link. But you can imagine a molecule absorbing infrared light, then those bonds that are moving can move more quickly. And then they release that light and they move more slowly. The different transitions are then associated with different amounts of energy. So, I wish I had a little more space here. What does it mean to have different vibrational transitions? You know, I am actually going to put in a new slide. Hold on one second. All right. So let's look at a molecule of formaldehyde. Oh. What's formaldehyde used for? What was that one? Killing things. Okay. I prefer to think of it from the scientific preserving specimens, right? We preserve specimens in formaldehyde so they don't degrade. It's a pretty simple molecule. It's got one carbon, two CH bonds, and one CO double bond. Now, these bonds can stretch. So that means like the C and the O can move away, like towards and away one another. Sometimes they can rock. So they'll move like sort of up and down compared to one another. They can deform. Yeah, this is how the atoms in the bond are moving. They can do something called wag. There's lots of different vibrational transitions that these can have. And each of these has a characteristic IR wavelength associated with it. Yes? Did I hear my name? Or am I just hearing things? Each movement. It's really hot in here. I might be hallucinating. Okay. So each movement has a characteristic infrared wavelength associated with it. So the major one here would be the stretch between carbon and oxygen in the double bond, and then the stretches between the C and the H's in their individual bond. So I shine infrared light on this sample. I measure what gets absorbed. These bonds will absorb specific wavelengths. The CHs will absorb a specific wavelength. The COO will absorb a specific wavelength. And by looking at that, you guys have this on your next page. Bonds in a molecule can be identified. So while I have taken a class in this, Mr. Hamill's the expert. This is a big part of organic chemistry, and he teaches that over the summer. So, for example, if he can look at this and tell you exactly what bonds are present in a molecule, in this molecule. So I knew that this peak right here meant that there is a CH. I knew that this peak here meant that there was a COO. I did not remember that this peak here was a C double bond. You don't need to memorize any of these things. These are just examples of how it's used. What you need to remember is, okay, infrared light can be shined on a sample, bonds absorb it, move in different ways, and we can identify bonds in the molecule from that. All right. So the next one, this is, I look at this, I can see, oh, it's got an OH bond, right? So this is a common technique that scientists use to try to probe the molecule to figure out what bonds are present. So we're using light to figure out the structure of a molecule. I think it's kind of neat. You'll spend weeks on this in college in organic chemistry. Here you get 10 minutes. Okay, but there's a very important part of this. How are infrared and heat related? There is a huge way in which infrared and heat are related. Sorry. That affects you and will continue to affect you more than it will affect me. Then it'll affect my children slightly more than it affects you. It'll affect your kids even more. Having a blank moment. Yeah, the greenhouse effect. You got it. You got it, the greenhouse effect. And I almost spelled it incorrectly. So most heat that radiates is infrared. Is the infrared spectrum. So we get white light from the sun. It gets absorbed by the ground or the school or by us or whatever. We'll release some of that in the form of infrared. Okay? Things tend to not get white hot. Things tend to not get white hot. And this white hot means it's emitting visible light. Now there is a cool simulation. I keep coming back to this website. So this is going to show you, this will help you visualize how the greenhouse effect occurs. We're going to run this. Keep. Okay. I think this will probably be just about the last thing we do today. We're almost done with this unit. Anybody have good plans for the weekend while we're waiting? Oh, okay, good. It's back. Sorry, I don't even get to hear. All right, so the sun is shining this visible light onto the Earth. The visible light here is the yellow, and we're shooting out infrared, which are the red particles. Now, if I increase my greenhouse gas concentration, so I have lots, what's happening is the molecules in the atmosphere are absorbing the infrared, and instead of letting it get released, what's happening? It's shooting it back down at the Earth. So what happens is the white light comes, gets absorbed at the Earth, emits infrared. With low levels of greenhouse gases, that infrared just gets emitted out into space. But with a lot of greenhouse gases in our environment, it absorbs the infrared and bounces it right back to the Earth. So it doesn't have to bounce right back to the Earth. Sometimes it'll bounce it back into space, but a lot of times it bounces back to the Earth. So what does that do to the temperature? It's going up. And as I increase to lots of greenhouse gas, we can slowly watch over time that the temperature is increasing. Right? So we need some greenhouse effect. The greenhouse effect is actually really important for us as humans. If we had none of it, then we wouldn't have enough heat to live. The global temperature would be really low. But if we have too much, well, then our global temperatures get too high. We get these weather effects that are really dramatic. There's in my former town of Boulder, they're having terrible floods right now. You can't always match one-to-one greenhouse effect in these weather events, but they're certainly happening much more frequently. Drought, we're having droughts that we haven't had in 100 years. So white light hits the ground, emits IR, IR gets absorbed and gets bounced back, and we continue to heat up and heat up and heat up. The cool thing here is let's drop it back and let's not be so morbid. Okay. Yeah, so let's do the Ice Age when we didn't have that much of a greenhouse effect. See how most of the IR is leaving? Very little is getting absorbed and re-emitted back to the Earth. Now today, do you see how that went all the way down to 42 degrees? I don't like that it's in Fahrenheit. So 283 Kelvin, it went down very low, and now we're bumping right back up to today. But you can put in cool things here. Oh, I can change this to Celsius. All right. I can add. I thought I could add clouds. Oh, all right, right there. So on a cloudy day, what's happening to the visible light? Some of the, not all, but some of the visible light bounces off. That's why on cloudy days, it's not as bright. The white light is hitting the clouds and bouncing off and going back to outer space. So it's not as warm, right? I just thought that this was a cool visualization. Yeah. What determines if something bounces out or not? So the photon has to hit the molecule in the right orientation to make it vibrate, and then it would have to relax and release it back down. So it's all about orientation and hitting the molecule. The more molecules you have in the atmosphere of a given greenhouse gas, the more frequent those collisions are. Turns out that CO2 is a really bad greenhouse gas. What is a worse greenhouse gas? So chlorofluorocarbons, that's an interesting sort of misconception. The CFCs are really bad for the ozone layer, which blocks the UV light from the sun, which is really important. But the chlorofluorocarbons don't have a huge impact on the greenhouse effect. They're methane is very bad. Methane is very bad. So cows release lots of methane. Very bad. I didn't even know termites apparently release a lot of methane. I'm learning things. This is awesome. So, what's that? So the bacteria in their guts release the methane. Yeah, liquid natural gas, you guys have heard about fracking, where they're just releasing tons and tons of methane into the environment. That's really bad for the greenhouse effect. Another really bad greenhouse gas is not one we would ever think about. Water. Water is a really strong greenhouse gas. So, what's happening when we get when we get more and more CO2, more and more heat's bouncing back to the Earth, which means more water is evaporating, which means we get more water in the atmosphere, which means even more IRs bounce back. So it's this, you've heard the runaway greenhouse effect, that could be what happened. But it's Friday and it's 2:19, so I want to end on a happy note. So that's why it's important to be environmentally friendly. I know. But we're in a good spot right now. It's a beautiful September Friday.